Hello and welcome to the session 4A on NLP. So let me introduce you to the session chair, Mr. W.V. Welgamer. He obtained his Bachelor's of Science degree in Computer Science Honours from Faculty of Science, University of Colombo in 2004 and has joined the Language Technology Research Laboratory, UCSC, as one of its pioneer members. While working on local language computing research in LTRL, he completed his master's degree in linguistics in University of California and master's of philosophy degree in computer science in UCSC. After serving more than 10 years in LTRL as a researcher, he joined UCSC academic staff as a senior lecturer in 2014. His research interests are computational morphology, computational linguistics, automatic text summarization, natural language processing, and text processing. Mr. W.V. Welgamer, I invite you to lead the session.
Okay, thank you very much, Kavinder. Hope you all can hear me.
Yes.
Okay, thank you. Welcome back to the day 2 technical sessions. The first session, session 4A in natural language processing. In this session, we have 5 papers, namely in paper ID, paper 24, 40, 25, 44, 65, 97, and 98. So hope all the presenters are here with us. So we will go one by one. We'll start with the first one, paper ID 25. The paper title is A Stochastic Part of Speech Tagger for the Sinhala Language Based on Social Media Data Mining. This paper is authored by Shalki Venushka Vitanage and Tushari De Silva. So both of are from the Faculty of Information Technology from University of Moradua. So the presenter today is Ms. Venushika Vitanage. So Venushika is Information Technology from University of Moradua. So we will listen for the presentation and then we'll go for the Q&A. So please start with the presentation. Your presentation. Then after 15 minutes for the Q&A, you can switch on the video and your mic and we'll join with the Q&A. First, we will move with the presentation.
Upcoming slides. We are the open word class and Nipata belongs to closed word class. Now let's discuss about the corpus. Corpus is a collection of machine-readable text which represent a particular natural language. In this research, we collected data from social media platforms such as Facebook and Twitter, and it consists nearly 10,000 words. Next, let's move on to the literature review. Sandaleka Fernando et al. Of CSE Department of University of Moradua have conducted a research on developing a SVM-based post tagger. To overcome the limitations of existing tagsets, a new multi-level tagset was developed. They have extended the UCSC tagset further based on contextual definitions or inflecting factors. This complete tagset consists of 148 tags. They have extracted the corpus from official documents used in different government organizations, and this corpus consists of 70,000 words. This tagger concerns about 3 features in tag generation. They are post features, word features, and lexical features. In the feature generation, a centered window of size n is considered, and the evaluation was done by changing the size of central window n. As per the evaluation results, the highest overall accuracy, which is 84.53%, was reported when n equals to 3. Let's move on to another research. Kant et al. Have conducted a research to compare machine learning and deep learning approaches for developing a post-tagger for the Urdu language. Models evaluated in this research are support vector machine, CRS, two areas of the deep recurrent neural network, and Bayesian hidden Markov model. CLE dataset and BJ datasets are used, and for training and testing purposes, CRF sharp libraries were used. They have used a tenfold cross-validation experiments. According to the evaluation results, CRF model has performed well in the CLE dataset and the LSTM RNN model has performed well in the BJ dataset. Here's a detailed description about the methodology. As you can see, this is the design of the HMM post tagger. This tagger has two main components, which is HMM trainer and the HMM trigger. First, a post-tagged single context is fed into the HMM trainer, and then those data are normalized and tokenized. Now, using those processed data, we can calculate emission and transition probabilities. In the HMM tagger side, testing dataset is the input, and then those data are preprocessed. Then for the Viterbl best path finder, both preprocessed test data and calculated probabilities are fed. Then the backtracer finds the correct tag sequence and output the result. Let's discuss these steps in detail. Normalization is the process of eliminating, formatting, and encoding problems in the corpus. When it comes to tokenization, it is the process of breaking down a text into tokens. For tokenizing the training dataset, white space is used as the delimiter. After tokenization, corpus is in the word dash tag format. Then these tokens are used as the input for the probability calculator. Now, let's look into the hidden Markov model in detail. The main goal of this HMA model is to compute the most probable tag sequence T hat of tags T equals T1, T2, T3 to Tn for a given word sequence in the sentence W equals to W1, W2, W3 to Wn. If we get the T hat into an equation, T hat equals to the first equation. But using the base law, probability of W given T is equal to equation 2. Therefore, T hat can be written as in equation 3. As we are searching for the most probable tag sequence for a particular word sequence, we can ignore the probability of the word sequence, which is PW. Then T hat can be written as in equation 4, where PT is called transition probability and P, T given W, can be called as M. Two assumptions were made to make calculations easier. First one is probability of a word depends only on its tag. Therefore, emission probability can be calculated from equation 5. Assumption is a tag only depends on the previous tag as we are considering bigers. Then the transition probabilities can be calculated as in equation 6. Therefore, finally, T hat can be written as in equation 7. Now, let's move on to the probability calculation. Emission probability can be calculated as in equation 8. That means count of occurrences of a given word with a given tag should divide with the total occurrences of the given tag from the corpus. Transition probabilities can be calculated as in equation 9. That means total number of ti minus 1, ti tag sequence occurrences in the corpus should divide from the total occurrences of the ti minus 1 tag in the training corpus. This research uses the Viterbl algorithm for the decoding task. Decoding means finding the post-tag sequence with the highest probabilities along the path for a given word sequence. The resulting tag sequence, also called the Viterbl path. Emission and transition probabilities are needed to calculate this Viterbl path. Next, let's look into the implementation. Data extraction. Basically, data was extracted from traveling groups and public profiles on Facebook and Twitter. Tagging the corpus. The corpus was manually tagged using the chosen tag set. Each word is tagged with the relevant post tag. An underscore was used to separate the word and the tag. In this slide, you can see a raw data snippet and the relevant tag data snippet. Now let's see how the probability calculation is done with an example. Let's consider the sentence ඉදල් ගස්සින්න පැත්තෙන් තමයි හිරු දාල් දිස්වන්නේ. Calculated emission probabilities are presented in the table, and the transition probabilities are calculated as in the slide. As in the diagram, from the start state, it goes to the NNPI state, as there is only NNPI tag associated with the word idal kasina. Like this, the algorithm navigates to states, and if we consider the word hero, it can has both NNN and JJ tags, therefore it has two states. T hat is calculated along the arrow paths. After navigating the final state, backtracing starts. From the end state, it goes along the path where the probability is highest. When the start date is met, backtracing stops. Then each word is tagged with the relevant tag. Now let's move on to the evaluation. Experimental dataset. The full dataset consists of 10,000 single words. Dataset was divided 80% for the training dataset and 20% for the testing dataset. Again, the training dataset was divided 80% for the training purposes and 25% for the validation purposes. Next, let's have a look into the evaluation metrics. The overall accuracy of the system is measured by comparing the tags proposed by the system against the actual tags. You can see the equation in the slide, and the accuracy of each tag can be measured using a confusion matrix as presented in the table. Using these four metrics, performance of each post tag can be evaluated by the following measures, which are accuracy, precision, recall, and F measure. Now, let's have a look at the experimental results. Accuracy of the system was measured for both known and unknown words. This study has shown 63% overall accuracy and nearly 90% accuracy for known words. System is evaluated with the unknown word percentage, as you can see in the graph. When the unknown word percentage is getting high, the total accuracy of the system is gradually reducing. Then we have evaluated each post for accuracy, precision, recall, and F1 score. All the results are presented in this table. In this slide, we have compared our HMM approach with the SVM approach that we discussed in the literature review section. When comparing, our HMM approach have performed well when compared to the SVM approach. The limitations. Tagging errors occurred during the manual tagging process has contributed mostly for the error rates in our approach. And the corpus used in this system limits only to the social media data. And this research only considered Python probabilities, so we did not consider the long distance relationships between tag sequences and words. Let's move on to the further work. Implementation of a rich tag corpus for single language would be useful in the future, and this system should be enhanced to calculate trigon probabilities, so it will contribute to the more accuracy rates in this approach. And integration of a morphological analyzer would be more useful. Thank you.
Okay, Venushika, thank you. That is a nice, clear presentation. So Venushika, can you switch on your video and the mic, please? So any questions from the audience? Now is the time for the Q&A. Meanwhile, Venushika, I have some questions.
Yeah.
Now, in the paper, you have mentioned that the social media data is not grammatical and not well placed. So in that case, why did you select social media as your data source for this research?
Yeah, actually, I did this research as a part of our final year project, which is a hotel recommendation system. In there, we intended to grab the social media data from users and analyze their intentions towards hotels and travel categories. That's why we have chosen the social media platform for this research.
Okay,
So
good.
how you deal with these errors in the, sorry, yeah, you go ahead.
Yes, yes, sir, you can continue. Yes.
No, how you deal with this, it's not grammatically correct. So if you get the data from newspaper, probably you have better data set. And so how you deal with these errors and unnecessary symbols, all these things, if you get a Facebook reviews and other stuff, it's not perfect, no? It's not good for this kind of work. So other thing is, that's just that's on it.
Yeah. Anyway, according to our research project, which is a hotel recommendation system, we wanted to get the user opinions about traveling and which categories they are interested mostly like those data. So uh, about the error rates, first we grab the data from social media platforms and we process those to remove unnecessary data. Actually, the parts we wanted to focus was the mostly the adjectives and verbs in those contexts in order to analyze their sentiments. The post-tag data was inputted to the sentimental analyzer in order to mine the opinions of the users. So as the answer to your question, to get rid of unnecessary data, we pre-process those data after we collected the data.
What is the size of your tag set? You use your own tag set, no? Tag corpus.
Yeah. We have used a 24 tag set, and the corpus is nearly consists of 10,000 words, which is a small corpus.
So would you think that 10,000 is enough to cover all the 24 tags in with sufficient frequency?
Yeah, I know it is a quite small corpus,
Okay.
uh, but as there are no existing corpus which is tagged using social media data, we have to collect from uh, beginning and tag them manually.
Yeah, but what is the issue of combining, I mean, using already existing tag data with this to just train the tagger? I mean, why do you particularly looking for social media text? Is there any difference with social media text and?
Yeah, the issue in there was with our project, we have modeled the architecture like this. There's a particular user, say me, and I post uh, some things in my FB account about traveling and the about the hotels I visited. So we wanted to, uh, if I am going to our hotel recommendation system going to mine my opinion, we had to collect data from my FB account and the
Yeah, but
public post I have put it.
the issue is that this particular task is to get the tagger accurate. So in
Yeah.
that case, didn't you try to merge existing tag data with your data and improve the accuracy of tagger? Then eventually it will tag your context data as well with more accuracy. Because in your table, you have values. Two is still missing. That may be because lack of data.
Yeah.
Okay, is there any questions? Any other questions from the audience?
Hello.
Yes,
You
sir,
hear
you
me?
can. Yes, we can hear you.
This is a good piece of work, but you mentioned about this contingency table, right? True positive, true negative, and so on. I am wondering how you counted the true negative in your work.
True negative means the
I mean,
tag.
you showed the table, right?
Yeah.
True positive, true negative, and so on. False positive, false negative. And so I'm wondering what is true negative? What do you mean by true negative in this research?
True negative means if we consider a word that has to be a verb, if we consider a verb category, it has to be, I think, the true negative to the verb category. If it is, but the tagger tags it as a verb, uh, It is a true negative.
How many count that as true negative?
I think that result is not presented in the slide. We haven't calculated those separately but using true negative and true positive values, we have calculated that precision recall and F1 score measures.
No, it is used just matched with the manual and result one, is it?
Yes.
Okay.
Okay, then I assume there are no more this particular session. So thank you very much, Venushika. Shall we all give him her round of claps by switching on your mic? Okay, thank you very much. We'll move to the next one, paper ID 44. Paper ID 44 is a legal party extraction from legal opinion text with sequence to sequence learning. This paper is authored by Melonidi Almeida, Chamodi Samaravikrama, Nisansa de Silva, Geetika Ratnayaka, and Amal Shehan Pereira. So all of are from the Department of Computer Science and Engineering, University of Moratuwa. So today the presenter is Chamodi Samaravikrama. She is a final year undergraduate student in Computer Science and Engineering Department from the University of Moratuwa. The study she will present today in ICTer 2020 is an outcome of her contribution to the project called Sigma Law, Legal Information Extraction at the Data Search Research Center of University of Moratuwa. So Chamodi, we will back to you with the Q&A session, and first we will see the presentation.
I will be presenting on legal path extraction from legal opinion text with sequence learning.
Anjali, we can't hear the sounds.
So the technical difficulties as usual. We'll wait another few, Anjali. Anjali, is there any issues? Okay, we'll come.
Sir, can you see us?
Yes, Sanjani, we can hear you and we can even see your screen, but not, now it's gone. Sanjani, we show your screen. We can.
Sir, shall I try sharing the screen?
No, I think now it's fine. No.
Okay.
Sanjani, can you play this? Yes, we can see the presentation.
The Cont extraction from legal opinion text with
Kavinda, did you ask to share the screen? Do you have the set or the?
Yes, sir, I have the presentation.
You mean the video?
So let's see. Anjali is sharing the screen again.
extraction from legal opinion text with
Anjali, sound is.
It's
very
not
low.
up at the moment.
Yeah. No, there's sound is there. We can hear very low sound.
Kavinda, could you please start that? I mean,
Yeah, Kavinda, you can try if you have the videos.
Okay, sir, I'll try.
If the audio is not audible, I can do the presentation live. Hello?
Yeah, Chamodi, yes, we can hear you, but it's with low sound volume.
So if the audio is not, like, if it's not very audible, I can do the presentation live if you don't mind.
Yes, we'll keep it that as the final option. First, we'll see whether Kavinda can play the video.
extraction from legal opinion text with sequence.
Sir, the sound is
Yeah, I
very
think
low.
that recorded video has very low sound. So Chamodi, if you have very good internet connection and if you confident that you can do the presentation live, yes. Can you do the presentation live, Chamodi?
Sure, sir. Give me a minute.
Yeah, try to stick the time for the 15 minutes. Now we are already 20 minutes behind the schedule. So Chamodi, you can share the screen and start the presentation live. I assume there would be no any connection issues.
Can you see my screen, sir?
No, not yet. Not yet, Chamodi.
How about now, sir?
No, still I can't see. I assume all of the others also can't see your screen.
Yes, sir, we can't see.
Harvind, can you guide her how to share? Chamodi, do you know how to share the screen?
So I clicked on the share screen and clicked on this, my browser icon.
So I think when you click the share, you get different apps and the screen. Harvind, in this meeting session, do we need to adjust some rights or set up in order to see this?
I think so, sir. I think we have to elevate her to a present, I think.
Anjali, please make the Shamodi as the presenter, one of the presenter in the meeting. Right?
Okay, yes. That means, yes, you have to be a presenter in order to share the screen. So in that case, Anjali, can you make Chamodi as a presenter if you have relevant rights?
I think all are in the presenter category.
No, yes, I am in the participant list. I can see all of us in the participant list.
Nobody in the team as a attendee.
No, but Kasun, nobody are in as presenters as well, I think. I saw in some session. Sorry?
I have allowed all of them to present.
Okay, then Chamodi, can you try it again?
On top, it says stop presenting. That means I am presenting, right?
No, we can't see your screen.
So it says presenting on the top now.
No, Chamodi, actually we cannot see your screen. Chamodi, shall we do in this way since time is going? I will, yeah, we will move to the next one while I will ask one of our assistants to contact you. And
Okay.
so once you are done, we will get it as the next one. Is that okay, Chamodi?
Yes, that's fine. Thank you.
Okay. Okay, the audience, sorry for the inconveniences due to the technical issues. We'll move to the next one while we postponing this paper ID 44. I hope next presenter is available, paper ID 65. So let me take the paper ID 65 is trending pattern identification of YouTube gaming channels using sentiment analysis. This paper is from Harshani Gajanayaka and TC Sandanayaka. Both are from Faculty of Information Technology, University of Moratuwa. So today is the presenter here is Harshani Gajanayaka, is a BSc student in Information Technology and Management faculty from the University of Moratuwa. So Harshani, we will get you online after your presentation is done. So Anjali, shall we play Harshani's presentation?
Hi everyone, I am Harshni Gajanayaka and the author of this research and the co-author is Dr. T. Sandanayaka. So today I am here to present my research about the trending pattern identification of YouTube gaming channels using sentiment analysis. First, I will give you some brief introduction that YouTube has become the second biggest and commonly used search engine and the place that contributors can earn money by uploading videos. In present, YouTube has become the social media leader in sharing and providing the content creators with videos. They successfully gain the monetary profits from the views and their content. YouTube encourage their creators to publish their videos and allow others to comment on the videos. That longer videos have that greatest number of comments most of the time. The highest number of comments and shares and views make the video go high, so that the ranking system will keep the channel trending. So this platform is localized in 91 countries and accessible in 80 languages, different languages. That the industry of watching other people's play video games continue to the surge in popularity. In 2017, that around 666 million people around the global tune into gaming video content made by fans and publishers, and that number is expected to grow to over 40 million by 2019. The problem of this research is that many YouTubers have the problem of that lack of awareness of making video trending. So that the YouTuber should follow suitable methods and practices to increase the views, follows, and subscribers amount. It is a difficult task to the YouTubers to identify the proper mechanism to predict the trending behaviors of the channel based on the views behaviors and the comments provided by viewers. As the views of subscription and comments are very much useful in popularizing YouTube, that currently there hasn't any methodology to predict how channels is going to behave in the future when coming that views and subscribers. The research objective is that first is analyze the YouTube data upon that pre-processing and converting into the dynamic metadata, and then create a classification of extract YouTube trending videos based on the
sentiment of viewers' comments. So in here we identify that videos are trending in the negative way or positive way. So we need to identify that. That's why we use that sentiment analysis for analyze the comments. And the third one is trending pattern identification of YouTube gaming video channels. In this research, I found some related researchers that they use they done some kind of YouTube analysis and the sentiment analysis. So most of them are use that that in the sentiment analysis they use that support vector machine and the random forest naive Bayes like that approaches. So first researcher that he this is that sentiment analysis treated as a topic-based text classification and used naive Bayes support vector machine, and they accurate the sentiment classification for spot. And the second researcher, they use that unsupervised lexicon-based approach to detect that sentiment variety of user comments in the YouTube. As the results also show that recall of negative sentiment is poor compared to the positives. So the third researcher, they analyze the sentiment of each comment and they are trending pattern using naive Bayes classification techniques, and they achieved an accuracy about that 81%. And the fourth one is they test their algorithms with Twitter data and discover that the random forest classifier offered that best results. And the fifth one, they analyze the sentiment model based on the YouTube comments using support vector machine. According to that, they use lexicon-based method for attitude analysis, and they achieve 84% accuracy from support vector machine classification. When go through the move to the our data set, the first is that extract the comments using export that YouTube API version 3, and the second being that pre-process such comment the prepare for the more effective sentiment calculation. This study that collect more than 1,000 of the trending YouTube gaming videos based on that selected countries from that API, and we filter the game videos data from this given game category ID and filter those videos metadata into the CSV format. In metadata, we got video ID, title, published time and date, and channel ID, channel title, category ID, and trending date tags, view count, like, dislike, comment count, thumbnail, comment disable, rating disables or not, and description also. But we can't get the comment in the but we need to get the comments in separately. So in particular comments had the ID, so we get the comment ID, comment and author, and like count and dislike count, and publish time and date. In the high level architecture, first we get the data from the YouTube API data, and then we pre-process. In the pre-processing part, we do that remove that stop word, stemming, lemmatization, part of speech normalization, and remove that that white spaces and like that things. And after the pre-process, we done the feature extraction using 4 method, that bag of words, TF-IDF, vector. And after that, analyze this that model, we classify that that comments using that logistic regression, support machine, random forest, and naive Bayes classification. And after that, we get the model accuracy and predict the sentiment result. In natural language process, we done that, we get the comment and we tokenizing that and remove the unnecessary words. And after that, we lemmatizing as mean, and then transfer into the binary format because that machine can't understand that words. So that machine can understand only numerical values. So that's why we transform that comments into the binary format, and we get that sentence are positive sentences or negative sentences. In the process of prediction, first we embedded the words from that get the API and the comments and use word to vector and document to vector methods, and we embedded words in the. After the feature extraction, we had training dataset and testing dataset. In the training dataset, we pre-process and we embedded that word embedding also, and after the feature selection and the preparing feature set and train classifier. In the prediction model, we get the testing data and training classifier data, and then we train the model. And this after predicting that model, we get the prediction accuracy of positive and negative, and then we input the results accuracy. We move into the methodology session. First one is the feature extraction. The feature extraction process is used to derive the features from the pre-processed data that can be fed into the machine learning model as the model expects numerical features. The feature extract can be done in the respect in the steps. The first step is that common specified features are extracted, and furthermore we analyze that emotions also. In that emotion can be positive or negative because many viewers are comment their emotions using emojis. So that's the reason we analyze that one also. They given different weights of emotions, we give that -1. So, and after extracting the YouTube comments in specific features that consider the simple text, and feature extraction can be performed by 4 main methods, and they are the back of first TF, IDF, and web embedding. In this research, I found that viewers expressing their ideas and their opinion in negative and positive way. That's the reason that using sentiment analysis for this research, and we can find that videos are trending in the negative or positive way. That is, sentiment analysis helps to understand people's opinions is better and more accurate way. So that it is very important part in this research to identify the reviewers' opinion and what they think and they expect from the videos. It can be positive, negative, or neutral. But people's perceptions are different from one another. So in this analysis, we identify some text are obviously positive, some text are obviously negative, and some text can contain that both positive and negative statement in the same time. So therefore, we need to analyze that comments using the label. In this sentiment analysis, we found that best approach to identify that we find that best approach using the sentiment classification, and the second one is we find that reasons for negative behaviors in the review more than positive reviews. So in here we get that gaming video. So there has many negative behaviors we saw. So that's why we analyze that one also. That in sentiment analysis, the investigation of breaking down the sentiment of text, frames, and mind and feelings from comforts text. So for the most part, this attempt to arrange bit of content into various classes objective. So abstract or spam or not spam, like that things. In the feature extraction model, it will train on the data using different algorithms. So that training data set apply to the result that obtain that feature extraction. That in the sentiment analysis, we use that training data set for classification. That Test data evaluate the accuracy of training modules sentiment outcomes as training algorithms that random forest logical regression, naive and support vector machines were used for evaluating the results. It applied the test data to train model and extract the features and classify the sentiment of the comments into positive, negative, or neutral. When compared with the existing systems, we found some that Agrawal and Mitas, they done some their system, their sentiment classification using road set based hybrid feature selection. So they get the 300 movie reviews, YouTube movie reviews comments, use that sentiment and predict. So they are therefore they use that random forest and naive bias classification, and that random forest was able to achieve accuracy in 60%, and the naive bias managed that 55%. In the results, that the calculation of accuracy level of analysis that for methods that result that we done using need to have accuracy, precision, and recall performance evaluation from the experiment with the confusion matrix method. And in here we select that naive bias classification. Because of that, naive bias that they got 80.4 percentages more than the support vector machine. And that other reason is that YouTube comments are short and often just a single or maybe a few sentences long. The reason is that we use that naive bias approach to suitable for our data set. In this table, that's showing that testing and training data accuracy level with the extraction algorithm and model training classification. That accuracy value is one of the estimation of that method used, and that accuracy of the data obtained from the data type is correctly classified according to the class of sentiment groups and total amount of data. But in here we can see that support vector machine perform well than the naive bias, because in the support vector machine perform more than 80%, but naive bias that average we that get from 60 to 80. So by the way, we select the naive bias. That other reason is that in the bag of Earth model that inherently highly dimensioned and instant very sparsely populated vector of that space, and that naive bias is widely used due to the efficiency and ability to combine evidence from more features. So that's reason we select the naive bias classification and bag of words method for our data set, and we select that this one is the best approach for our system. And moving to the training pattern analysis, here that study we able to introduce new features to the user to feature analysis on metadata and giving recommendation. So that trending pattern analysis we conducted through the collection of the metadata in the dataset and analyze the Python libraries of pandas and matplotlib. In this dataset collection, we get from 2-month trending video games based on that USA trending list. According to this research, that we get that length of title and video view count, video publishing time, hour duration, and day in the week can be factor for that video becoming trending. It will be helpful new YouTuber who is entering the industry to follow up with best practices to treat in the industry. In the first image, first graph that show that trending date and number of videos. We found that many videos are published on that Tuesday, and it is between 50 to 60. And the next feature analyze that topic of the video that in the second image, that title, length, and number of videos. This study recommend that new user to create topic which is relevant, meaningful, and attractive and creative. So user get attached to the topic simply because of their curiosity and interest. This study found that many trending game videos had 40 to 60 characters approximately. And the third image is that publishing hours and number of videos. And many trending videos are published at 5 p.m. to 10 p.m. And the reason of that, because many game players are uh, watches that after 5:30, and they would like to spend their free time playing games and watching the game videos. And finally, that most important topic is that quality of the audio and video. Uh, we can't get that. We couldn't analyze, but in the research we found that the audio and the video should be clear to the audience. It should be matched with the content, and the same time that audio clip has have very good flow in telling the story, hence that audience get attracted to the videos. And the last one is that, and we found that reason for negative behaviors of the comments, so reviewers more than positive reviews. Because of that, of the reason is that keyword in the gaming videos, they are, as example, they use that kill, shoot, destroy, die, like that word. So, and the other thing is sarcasms also. These are the reasons for that videos are trendy with in negative way more than the positive way. In the future was we had to analyze that sentiment analysis model has negativity behaviors of the comment analysis. That should be researched more than improve the solution and combine with the system and analyze the sarcasms and remove these comments from the comment list and analyze the comment sentiment for trending videos over the time, then improve the prediction accuracy. And these are the references. And thank you for listening my presentation. And we move into the Q&A session. Thank you.
Okay, thank you, Harshani. Can you switch on your microphone and the video, please? And the audience, if you have any questions, you can ask now. Okay, meanwhile, audience is wrapping up the questions. Harshani, I'm a bit confusing. So did you get that trending analysis based on your sentiment result or from the features?
That I analyze sentiment analysis for, because I need to analyze that comments that viewers, they put their opinions that many I choose that gaming video. So there, so many gaming videos are that trend with the negative way. That's the reason that they are the keywords. So in the comment section, I choose that get the opinions of the users, that viewers.
Yeah,
and
but
then
Harshani, that getting opinion is a different one. We call opinion mining. But in your case, you sentiment analysis, you had only 3 classes, namely positive, negative, and neutral. So if you mine opinions, yes, that can be different. But having with those 3 classes, how did you get those trendings? And do you think that the relationship between the good comments and the published date has any relations? Like if the video is published on Tuesday, will it get more good comment? Will it mean that it's a good video or something? Are you trying to say something like that?
Yeah, in that data set I get from the USA data. So that in then USA game video YouTubers are that publish more videos in the Tuesday. The reason is that they that after 5:30 that players are free and they like to watch that video. So
Yeah,
I
but
think
still,
that
can you say that would be a good feature of the video? Anyway, that published time and date would affect to the quality of the video, because you are overall talking about in here you said that the most important trending video related to user video types and show up what are the most trending videos which user will want to see. Then your objective is to give comments for the YouTubers to make good videos. So would you recommend to publish it on Tuesday after 5:30 p.m. as well as one of your findings or something?
yeah, that's I find I analyze that data, the metadata using that pandas libraries, and then I get that many videos are trending that uploaded in that time.
Be a coincidence, or I mean, yes, there should be definitely a day which have more videos, isn't it?
Yeah.
Okay. Anyway, any other questions from the audience? Yeah. Since we are far behind the schedule, I think we have to move. So shall we clap to Harshani and say thank you for the presentation. Thank you, Harshani. So we'll try to move to the missed presentation, which is paper 244. I think Kavinder, did you get the presentation slides? Then
So yes, sir. I got the presentation slides and I was able to amplify the voice of the video. So let's try that first.
Good, Kavinder. Shall we play the video then?
Okay, sir.
Then Shamoli be ready after 15 minutes for the Q&A.
So in the country, the very basic way of forming a law.
Can you carve in the play it from the beginning?
A bill is presented and passed by. Good evening, everyone. So I will be presenting our paper on legal party extraction from legal opinion text with sequence learning. So in the country, the very basic way of forming a law is through legislations where a bill is presented and passed by the authorities in charge, that could be the senators or the parliament or whoever. But even after forming a law undergoing the due process, there still can be several ways to interpret a law when you're trying to apply it to a practical scenario. So this is where case law comes to be. So case law is basically a collection of past legal decisions written by courts and similar tribunals in the course of deciding cases. And the legal principles used to resolve disputes in previously decided cases are used as precedents to decide cases with similar legal issues in the future. So with the setting as such, there comes a problem where the lawyers and legal officials have to study the existing cases to be used as precedents, and going through these cases similar to the ones on trial is expected of the lawyers. So as you can understand, this is a very tedious task because of the amount of documents available out there and the time and effort required, and also the potential threat of human error. So this creates a necessity of an automated system to handle the analysis and searching of the existing records with a natural language understanding approach. So this sets the motivation for our research. And in building such a system, when extracting information out of documents, we observe that identifying the legal parties is a task of very high importance. So what you see here is how a legal document is structured. So the most important element in a legal document is a decision, and there are two parties involved in a lawsuit, namely the petitioner, plaintiff, or the defendant. So petitioner is usually the person who files a lawsuit, and defendant is the person being sued against. And as you can see, all the arguments and the counter arguments discussed in the opinion text is stemming out from these said two parties. So it is very crucial in the process of extracting information to identify these two parties properly. What you see here is an extract from an opinion text. The case was Lee versus United States. So in this case, you can identify Lee as the petitioner and United States and Lee's attorney as the defendant. So these two clusters together, we identify them to be legal parties. That is Lee, United States, and Lee's attorney. So with our research, our paper, what we're trying to do is to identify all of these parties in general, like any legal entity that belongs to either the petitioner class or the defendant class. So output of our system would ultimately be these legal parties, the cluster of Lee, United States, and Lee's attorney. So to sum it up, why our research is needed, one is because identifying legal parties is the initial step of structuring legal documents to extract information. And as you could see in the previous slide, each legal party set may include multiple entities. And also in addition to that, we believe that our research would be helpful to other ongoing researchers such as party-based sentiment analysis, because to perform party-based sentiment analysis, you need to have the parties at hand. But in achieving the task, there are a couple of challenges we identified. The very first one is the complexity in the language used in the legal domain. So what you see here is an extract taken out from an actual opinion text. So even though this is out of context, you can see that there is a very native style of writing to this text. And also, most of these are very complex sentences. And even for a human who doesn't have any prior exposure to these documents or not very familiar with how the language in the law and order domain works, might have a little trouble understanding the information. So that is one challenge we're facing. And the second one is the ambiguity in identifying legal entities. So as demonstrated by this example, in the sentence 1, President Lee moved to the United States from South Korea with his parents when he was 13. The term his parents it turns out that his parents is not a legal party. That means it does not belong to either the petitioner class or the defendant class. But in the sentence 2, his attorney turns out that he is actually a legal party. So just because an entity is a person, you really can't say he or she is a legal party. There is a certain ambiguity in identifying those entities. That is another challenge. And the final one was the domain-specific behavior in the language used in the legal document. So what you can see here is a named entity recognition performed. We performed this using the Stanford NER tagger. And here you can see that Lee is identified as a person and also Strickland, but the government, when it comes to law, it sort of acts as an organization, but with the existing NER tools, it is not really recognized as an organization because it's a very domain-specific behavior. That is also another challenge. So now we will take a look at the related work. That is, there were a couple of technologies and tools we incorporated in designing our solution. The first one is the name entity recognition. That is the task of finding and classifying names in text. So I've demonstrated what named entity recognition is through an example. So as you can see here, the European Commission is an organization, France is a location, Britain is a location, and so on and so forth. So basically, named entity recognition is tagging an entity basing on a predefined set of classes. These set of classes can be anything. And another technology we used was the co-reference resolution. That is basically identifying all mentions that refer to the same real-world entity. So if you can take a look at the example presented here, all the terms highlighted in yellow, the terms Barack Obama, his, and he, they all refer back to the same person, which is Barack Obama. And the terms highlighted in blue refer back to the person Hillary Rodham Clinton. So what coreference resolution initially does is that it creates a sort of mapping and creates a cluster to identify all the tokens or the mentions that are referring to one single entity. So when we were trying to incorporate these two tools, the coreference resolution and the NER, we identified two major high-performing tools out there that were the Stanford and the Spacey. So when we wanted to choose a tool out of the two, we decided to carry out our own experiment and to choose what's best for us. So we created a data set of 20 sentences, and we did the coreference resolution and also the NER tagging manually. And also we performed the same thing with the use of the tools, and we calculated precision recall and F1. And as you can see in the NER tagging, the Stanford clearly outperformed Spacey. And also in the coreference resolution, even though the precision was a little lower, the recall was quite high. And we decided to proceed with Stanford because we thought recall is of high importance than precision, since in our model, the coreference resolution is happening at a very basic level, and in the coming stages, it is getting like more trimmed and pruned. So we believe that having higher recall is more important than having higher precision. And the other technology we used was the sequence learning with neural networks. So deep neural networks cannot be used to generate sequences using input sequences. And our inputs were very small paragraphs of sentences. So those were input sequences, and a multi-layer long short-term memory can be used to map the input sequence to a fixed size vector, and another multi-layered STM can be used to decode the output sequence from the vector. So to demonstrate it by an example, what we give the input sequence would be Parishana Jaili moved to United States from South Korea, and the output sequence 111 and 0. So like there would be a digit for each word or rather the token, and if that token is a legal party, the output would be 1 and 0 otherwise. So this is the overall structure of our solution. We first have the Cont sentence, and we send it to our first model, that is NER filtering model. So there we first identify person and organization entities with the use of NER, because we believe that we observed actually that a lot of the times these entities who are identified to be legal parties are either a person or an organization. So our first step is to pick and choose the person and organization entities. That we did with the NER filtering model, and with the use of coreference resolution, we edited the court case sentences by adding a mask on top of it. And then we had our sequence learning model. We sent the cases to training, and then also it would output a binary sequence, that is a sequence of 1 and 0s, 1 referring to a legal party and a 0 to an entity that is not a party. So in the process of designing this NER filtering model, we encountered a problem that was, as you can see here, so if you're performing NER from a tool that is out there, NER is performed to a single token. So for an instance, if you give the sentence Barack Obama nominated Hillary Rodham Clinton, Barack is identified as a person, Obama is identified as a person. But Barack Obama as a whole is not identified as a person. So to overcome this issue, we came up with our own algorithm. That is, we sequentially check for NERs of each token. And if consecutive tokens have the same NER, we identify them to be a single multi-token term. So the output of our model, the NER building algorithm, was that we would identify Barack Obama as a person, the whole multi-token entity as a person, and Hillary Rodham Clinton, the whole entity as a person. So this is how our masking worked. If we give the court case a text, petitioner Jaili moved to the United States from South Korea. In 35 years he has spent in this country. He has never returned to South Korea. In this, we first perform the NER. That is, we identify that petitioner Jaili is a person, and then we perform the court resolution by which we identify he, and he is referring back to Jaili, and then we mask the sentences. So when creating the mask, we use a dollar mark at the beginning to denote that this is the masking, and we use the letter P for a person and the letter O for an organization, and that is followed by a digit 1, that is to identify this is referring back to a particular entity. So the expected output of this is a sequence of ones and zeros. This is another example. So here James killed Robert, then he ran away to New Hampshire. We first identified James and Robert to be person entities and he to refer back to James. So James gets the mask $P1 and Robert gets a mask $P2 because it's a different person. And but the expected output is actually 100. We expect Robert to be 0 since he is not a legal party, even though he's a person, he's not a legal party. So to sum it up, our NER filtering model, first the court case sentence is sent to the Stanford annotator, and it performs the NER and the COREF respectively, and it gives the NER values to our NER build, and by using our algorithm in the model, we create a dictionary, a prefix dictionary, and with edited token list. And then we mask the text using the COREF values, and then we output the mask sentence. This is basically what happens inside our NER filtering model, the masking. So before sending it to the sequence learning, we do a character embedding. That is, we create a sorted set of all the characters in the data set, and the characters of the text is replaced with the index of above set. So the embedding we use is actually character embedding, and this is actually why we are using a $sign in front of the mask. So that gets a very specific value when we're embedding. So this is our sequence learning model. In the encoder part, you do the character embedding and the encoding, and in the decoder part, each output in each cell would be the input for the following cell, like how this is basically how it works in LSTM. So this is how our NER filtering model performed by its own, only considering the NER filtering model, not the whole model. So in identifying person entities, it had a precision of 0.93 and organization 0.93, and recall and F1 as presented here. So this was the performance of our overall model, that is deep learning approach with character embedding results. So we trained our model for 2 cases. First, we used without the mask, and then we masked and did the training again. And the data set we used for this training was 200 sample sentences from actual legal documents, and we manually annotated with output sequence of ones and zeros. And we trained the model, and we calculated its performance in terms of precision, recall, and F1. And you can see here the mask layer, the mask model clearly outperformed the non-masked model. So hereby we conclude our paper with our hypothesis being true. That is, 1, the sequence-to-sequence learning is an effective approach for extraction of legal parties from opinion text, and also that masking the person organization entities outperforms a model trained with non-masked entities. with respect to the model we created. Thank you for listening.
Okay. Thank you, Chamodi. Can you switch on your video and the microphone? Audience, you can ask any questions from Chamodi if you have any. Chamodi, are you there?
Yes, can you see me?
We can't see you and we can't hear you properly. Chamodi, can you?
Hello?
Yes, your microphone sound is low. Anyway, we can hear you barely. Can you switch on your video? Okay, Chamodi, I have a few issues. So you have used NER techniques for your research, but since this is English, there are well-established NER systems and methodologies, especially the tag like IBO tagging, which is famous for NER systems. So those would solve the issues you mentioned, like getting Barack Obama as a single named entity. So why did you try such existing research? I mean, well-known algorithms in named entity recognition for your research? Chamodi, can you hear us?
Yes, I can hear you.
Yeah, but we cannot hear you, Chamodi.
Hello?
Yes, speak aloud. Did you get my question?
Yes, sir. We were not actually very familiar with this IBO technique.
Yeah, IBO is a standard tagging standard way to tagging NLP, NER data, that is in beginning, in and out. So when you tag your data set with that IBO tagging, especially for NER, then you will actually it's the standard way to tag named entity recognition task. So since this is for English, what is the difference between this legal entity detection and other entity detection? And as the other question is, can't you do this as the techniques like information extraction, not retrieval? I mean, template filling like thing. Is there any format for these legal documents anyway?
So that's the issue, sir. So these legal documents comes in very like different types of formats. And what we are trying to do here is specifically perform this extraction on opinion text. So there is a certain, hello?
Yeah, we can hear you, Jamal.
So there is a certain type of documents called opinion text when it comes to law. So there, what you get is basically the opinions of the court and also the lawyers involved in the case. So there, they refer back to like let's say this particular hearing is regarding a case, and there are like evidences coming out from different court cases, different hearings. So they refer back to them also. So it's not very clear to like, you have to go through them and identify who are the parties there, and it is not presented in a very clear format.
Okay, Chamadi, thank you. Any other questions, please? Okay, since not now, since we are, I think 30 minutes, more than 30 minutes behind from the schedule. So let's thank Chamodi in the usual way. Please clap her with switching on your mic. Thank you, Chamodi. Okay, we'll move to the next one. Paper ID 97. The paper title is a comparison of transformer, recurrent neural networks, and SMT in Tamil to Sinhala machine translation. So authors of the paper are Ashmari Pramodya, Dr. Andil Pushpananda, and Dr. Wan Veerasinghe. All are from University of Columbus School of Computing, the Language Technology Research Laboratory. Ashmari is an undergraduate of UCSC who will be graduated in 2021 in Bachelor of Computer Science. Her research interests including machine learning, deep learning, and natural language processing, mainly focusing on low resource languages like Sinhala. So Ashmari, we will back to you after 15 minutes presentation. So be ready for the Q&A after 15 minutes. So we'll move to the presentation.
Hi, I'm Ashmari Pramonta. My paper is a comparison of transformer, recurrent neural networks, and SMT in Tamil to Sinhala machine translation. I'm presenting this on behalf of Language Technology Research Laboratory, University of Colombo School of Computing. So let me give you a brief introduction to machine translation. Machine translation is the task of automatically converting one natural language into another, preserving the meaning of the input text. So, if you go back to 1950s, rule-based machine translation emerged as a result of World Wars. Here, rule-based machine translation need expert knowledge of linguistics to specify the translation rules, and then came the corpus-based machine translation. Here they have two approaches, example-based machine translation and statistical machine translation. In SMT, it works by referring to statistical models. One is translation model learned from parallel bilingual corpus and language model learned from target monolingual corpus. Now, the emerging research has turned into neural machine translation. In 2014, sequence-to-sequence learning with neural networks was one of the first to introduce encoder-decoder model for machine translation, more generally known as sequence-to-sequence. Here, the encoder is used for understand in the source language, decoder for language understand in target. Here, each word in the sentence is fed separately to the encoder, and then encoder encodes it to a fixed size context vector, and decoder decodes the output. In the paper on the properties of neural machine translation encoder-decoder approaches, they investigate the limitation of the proposed model. They found that NMT performs well in short sentences, and when the sentence length increase, the performance degrade. They provide a visual graph in their paper regarding that. And to address that issue, in 2015, neural machine translation by jointly learning to align and translate paper introduced a new mechanism named attention. Attention was born to memorize long sentences. Here the key idea of attention is, instead of building a context vector from last hidden state, new architecture create context vectors for each word. So RNN is hard to parallelize. So attention all you need paper introduce a new architecture which is known as transformer. It is entirely based on attention mechanism, dropping the recurrence. It consists of stacked encoders and decoders. Unlike RNN, its transformer handles entire sentence at once. So NMT being competitive with recurrent neural networks and transformers, our study focused on how do the recurrent and transform architectures compare in terms of general translation quality in Tamil to Sinhala translation direction, where Sinhala and Tamil are low resource and morphological rich languages. And then we compared it with the statistical machine translation results. So the steps are given here. First step is data preprocessing. We use three representation: full word form, segmented with morphism, and segmented with byteband encoding. And training was done using LSTM and transform architecture. Next, we evaluate the models using BLUE score. And finally, we did analysis with the output of three approaches. In order to provide an accurate comparison with SMT, we took the same parallel corpus as using the early study in statistical machine translation. So the corpus details are given here. So the data preprocessing was done using three-word representation. First one, full word form. And in order to address the morphological richness of Sinhala and Tamil, we explore the impact of two subword segmentation methods. One with segmented with the morphism and one is segmented with the byteband coding. So in the second segmentation, we use the sentences segment with the morphism toolkit in order to make the post-processing easier after translation of subwords. We use the method proposed by a study. We introduce a special character added between subwords such that the boundary of the words are maintained. Then after the translation, the words can be put back to the original word form by merging each subword with a special character with immediately next subword. So as of the third representation was obtained by pre-processing the full word corpora using the algorithm byteband encoding. This algorithm requires a tuning of number of merge operations, which is an input parameter that based on the language and the dataset. To examine the impact of merge operations in translation, we did some experiments with different merge operations. We empirically choose value 5000 for Tamil to Sinhala translation as the number of merge operations. For our training, we use OpenNMT toolkit, which is implemented using PyTorch deep learning framework. It is an open source ecosystem for neural machine translation. Here we experiment with different train steps, and the hyperparameters we used in LSTM and transformer models are given here. So when come to the results for three-word representation, the blue colored table shows the blue scores reported by three-word forms. Looking at the blue scores, it is evident that the transformer performs better in all three forms. We examine the out-of-vocabulary percentage of each representation. For subword strategies, out-of-vocabulary present decrease significantly. That means subwords expand model coverage rapidly, increasing the number of words model can see during the training. So this has positively affected in increasing the blue scores. So another observation is byteband encoding performs better than morphism in both LSTM and transformer. In order to compare NMT results with SMT, we will be using the model trained with byteband encoding. Because system operating with byteband encoding shows significant improvements over others. So looking at the results, it is evident that transformer performs better than RNN-based models. For the small dataset we have, statistical machine translation performs better than transformers according to our observation. So to see what has happened there, an analysis was conducted for the translated outputs of the three approaches. The analysis shows that a lower target out of vocabulary resulted in higher blue score for SMT over transformer, where blue score values are calculated over n-gram matching. Words that have been translated to synonyms and incorrect alignments of phrase pairs will reason to have target out of vocabulary. Another observation made here is there are new words in the translated output that model has not seen during the training stage. So we did a comparison of the translated output sentences. The blue color highlighted word shows the exact word. Gray color word shows the translated synonyms, and yellow color words shows the word segmentation issues, and red color shows the untranslated words. So if we get the first example, it's a case where transformer performs well over SMT. Although the exact word is not predicted, the semantic meaning is represented correctly. So in the second example, it's a case where SMT do not identify the word Janadipati, which is a frequent word in the training model, but LSTM and transformer predict it correctly. And third case is a case where all the three approaches fails to predict the correct meaning. Only few exact words are translated. And in example 4, it's clear that the meaning of the transformer predicted sentence is similar to reference when compared with SMT. But most of the words transformer predicted contain synonyms. From all these examples, many sentence words have been translated to synonyms, which cannot be evaluated through BlueScope. So if we can do automatic evaluation with more than one reference translations per input sentence, we can obtain high evaluation score since it compares with synonyms. However, it's really difficult to obtain more than one reference translations for low resource language like Sinhala and Tamil. Achieving a higher performance for Tamil to Sinhala machine translation is challenging for various reasons, such as morphological richness and being low resource. So when we compared our results with resource-rich language results, it is low. However, reaching those resource-rich language results is a big challenge. We will need more effort in the future for improving these results. Thank you. Hi, I'm Ashmari Pramonta. My paper is...
Okay, Ashmari, nice presentation. Can you switch on the video and the microphone, Ashmari? Is there any questions from the audience?
Video and the mic.
Sir, I have one question.
Yes.
May I ask?
Yes, Rangana, go ahead, please.
So, Ashmari, you have done a very interesting research work. You are dealing with the converting the Sinhala sentences to Tamil, right? And you consider about the synonyms, but there is another case that means there are Sinhala words which may have more than one meaning, right? When we take an example from English language, let's take bank. So the bank may be a river bank or the place that we deposit our money, right? Likewise, in Sinhala, let's take Wanayak may be a forest or a tualayak, right? So likewise, there may be words which may have more than one meaning. So do you deal with that issue as well in your research?
Yes, we are focusing on Tamil to Sinhala direction. Here we, in the transformer, it use self-attention. In that mechanism, when we give a sentence, it refers, if you say that one word, vanya, it refers how it refers to other words in that sentence. Likewise, self-attention has multi-headed attention, means multiple heads collect self-attention. So it has multiple ways in the sentence how each word refer to other words in the sentence. So it's deal with in that way using self-attention mechanism.
Yeah, that means you according to the context you are dealing with it, right?
Yeah.
Okay, fine.
Okay, thank you, Rangana. Quick question, Ashmari. Now you have do this with nearly 25,000 data, as you said. So any idea or any plan to improve the data set and do the research in the future, or how do you think about improving the data set?
Yes, sir. dealing with that problem, we are going to increase the data set and do another research. They have collected, when referring to research papers, we have seen that they have used a Bible corpus and some parallel corpus they are in, we can get from the opus and some sites. So we are going to collect those and we are going to deal with that, add the Bible corpus into Sinhala and Tamil, because other low resource language use that Bible corpus like that.
Okay, thank you, Ashmari. Any questions? Okay, since the time is we are behind the schedule, let's thank for the author and the presenter. So thank you, Ashmari. Please give a round of claps for Ashmari. Okay, we'll move to the final one. We are behind the schedule. The final one, paper ID 98, is the impact of using pre-trained word embedding in Sinhala chatbots. The authors of the paper is Bimsara Gamage, Randil Pushpananda, and Ruwan Veerasinghe. All are from the Language Technology Research Laboratory at the UCSC. So our presenter here, is Bimsara Gamage, is currently a research assistant at the Language Technology Research Lab at UCSC. He received his bachelor of degree from Sri Lanka Institute of Information Technology, SLIT, and his current research interests include machine learning, deep learning, and natural language processing, and conversational agent technologies. So we'll go with Bimsara's presentation first, and then we'll go for the Q&A.
Hello, thank you all very much for giving me this opportunity to present my research. I'm Bimsara Gamage. I'm working as a research assistant in Language Technology Research Laboratory in UCSC. Now I'm going to present to you the work I did for the submitted research paper ID 98, the impact of using pre-trained word embeddings in Sinhala chatbots. Co-authors of the research paper are Dr. Randil Pushpanand and Dr. Ruwan Veerasinghe. First, I start with explaining what we mean by using the term chatbot. We also use the word conversational agents to refer chatbots. A chatbot is a computer program that simulates human conversation, which can provide instant answers for the human who interact with the chatbot within a short period of time. Popular examples for chatbots available in the internet are Google Assistant, Amazon Alexa, and Apple Siri, without leaving customers waiting. In addition, chatbots greatly increase the reach of a business to a customers, which is practically impossible with human labor. We thought the research on conversational agents for local languages is very important because even though huge amount of resources are available to develop chatbots for English language, when it comes to local languages such as Sinhala and Tamil, we couldn't find satisfactory amount of resources to develop and improve chatbot for these local languages. That was our motivation to do research on conversational agents related to local languages. As the members of Language Technology Research Laboratory, it is our goal to enabling language technologies to local languages. And one of our projects is developing conversational agent interfaces to local languages. When we are working on this project, one of the major obstacles we faced was finding training data to train chatbots developed for local languages such as Sinhala and Tamil. You know, the improvement of accuracy of machine learning and deep learning based applications mainly depend on training data used to train this application. The more data is used, the better the result in most cases. Because of the difficulty of finding training data, we had to think of a different approach to improve the accuracy of the chatbots we developed. Using word embedding in chatbots to improve the accuracy of them is one of a way to do it. I'll give you a brief introduction about word embeddings to get everyone's knowledge on the subject to the same level. Word embedding gives us a way to use an efficient dense representation in which similar words have a similar encoding. This encoding is trained on a huge amount of training data and could be able to capture fine-grained relationships between words. These relationships are used during the training of chatbots to improve the accuracy of the intent classifier of the chatbots. Since we haven't seen research papers on the subject of evaluating the impact of using word embedding in chatbots developed for Sinhala language, we wrote this paper discussing the methodologies we use and the evaluation of them and the result we observed. Before jumping to the methodology section, I start with little bit of background works related to chatbots. Chatbots can be classified into two main types depending on the technologies used. These categories are rule-based chatbots and machine learning chatbots. Rule-based chatbots have used technologies such as parsing, pattern matching, AIML, ChatScript, and finite state machines. Chatbots based on machine learning mainly use artificial neural networks to train their models. When it comes to comparing chatbot development frameworks out there, Google Dialogflow, Louis AI, and Wit.ai are the main chatbot development frameworks that provide services on a pay-as-you-go basis. Whereas the Rasa framework is the most popular open source solution for chatbot development and deployment. Developers who wish to use custom languages or multilingual training examples and want to have the leverage of open source technologies have to use Rasa open source framework in order to have maximum control over their chatbots. Because of the customizability and flexibility, we use Rasa open source framework to develop our chatbots. This framework uses different components to handle different parts of conversations. The name of the natural language understanding model of the Rasa framework is Rasa NLU. Rasa NLU is responsible for identifying the meaning of the user messages in the conversation. Rasa NLU works as a classifier which categorizes each and every user messages into predefined intents of the chatbot. What we wanted to improve using word embedding was the intent classification of this Rasa NLU component. Our approach for this research was training chatbot models using two different datasets with and without using pre-trained word embeddings to see the result we observed in one dataset also persist on the other dataset. Though we could see a clear improvement of intent classification of the Rasa NLU when we use pre-trained word embeddings to train the chatbot model, we wanted to make sure this was the case with other datasets. So we used two different datasets in our experiment. One was an open domain dataset and the other one was a domain specific dataset. Open domain dataset consisting of Sinhala small talk data, and domain-specific dataset consisting of training data related to banking domain. As the pre-trained word embedding, we use Sinhala word embedding available at fasttext.cc. Fasttext is a library for learning of word embeddings and text classifications created by Facebook's AI Research Lab. The word embedding trained on command crawl and Wikipedia data and consists of 808,044 vectors. Since RASA only support pre-trained word embeddings from SPACY and MITIE, the fast text word embedding has been converted to the SPACY compatible word embedding. There are multiple intent classifiers available in RASA NLU, but only the embedding intent classifier and diet classifier allowed to use word embeddings in the training process. Due to the reason that embedding intent classifier is deprecated by RASA, we use diet classifier in this experiment. This classifier is the recommended classifier by RASA team, and the neural network architecture of the classifier built based on the state-of-the-art deep learning model transformer, which is introduced in 2017. Since this study is not focused on evaluating the accuracy of the intent classifiers, but the impact of using word embeddings to train an intent classifier for chatbots, using only a single intent classifier to conduct this study can be justified. Each trained chatbot model was evaluated using 5-fold cross-validation. Cross-validation was used to evaluate the chatbot model because there were not enough training examples to divide the datasets used into training and test sets. As you can see in the above comparison table of each chatbot model evaluation, when using pre-trained word embedding to train chatbot models, show high accuracy in intent classification and positive improvement compared to the baseline model. This slide shows two intent prediction confidence distribution histograms. When we comparing the intent prediction confidence distribution, the lighter color bars represent correct intent predictions while darker color bars represent incorrect intent predictions. Shifting correct intent predictions towards the right side of the histograms while decreasing incorrect intent prediction by shifting them more towards left can be considered improvement of the intent classification task. Histograms of figure B and figure D, where intent classifiers use pre-trained word embeddings. We can observe above behavior in the figure A and figure B shows evaluation made with chatbot models trained on banking domain dataset, in which figure B shows fewer intent prediction errors and a corresponding improvement in the number of correct intent predictions with higher level of confidence. Figure C and Figure D shows evaluation made with chatbot models trained on Smalltalk dataset, where we can observe similar kind of behavior as in Figure A and Figure B. Overall, for the same dataset, fewer errors in intent prediction and an improvement in the number of correct intent prediction with high confidence are displayed when using the pre-trained Sinhala word embedding to train the chatbot's intent classification model. Evaluation shows that the use of pre-trained word embedding in chatbot developments leads to improvement in the accuracy of the intent classification model of the chatbots. In the future, further experiments can be carried out by increasing the number of training examples in the dataset to determine if the above results remain consistent. We also expect to test the performance of the name entity extraction task with and without pre-trained word embeddings. We have to give special thanks to the input of staff of the Language Technology Research Lab at the UCSC and to the staff of the IT division of the Bank of Ceylon for the support given to the research related to the use of Sinhala in conversational agents. If you have any questions, you can ask them now.
Okay, thank you, Bimsara. Can you switch on your mic and the video, please? Any questions from the audience? Okay, Bimsara, you said you trained word embeddings, but is that the one, the data set used in that particular tool, or you selected a corpus to develop the word embeddings for Sinhala?
Actually, I didn't train word embedding. I used word embedding available in FastText site.
But yeah, how about the data set they have used to develop the word embedding for Sinhala?
They use Wikipedia data and Common Crawl dataset.
Have they mentioned about the size of the data set?
Yes, in their site they have mentioned it, but I don't remember the exact.
Can't we use our own data set like UCSC corpus with 10 million corpus or whatever the things to create the word embeddings and test this?
Yes, we can, if we want, we can train our own word embedding and test the results.
So do you think that that will improve the results because of the more data set? I mean, if we assume that having more data giving more better word embedding for Sinhala, then eventually will it helpful to improve the accuracy in your chatbot?
Yeah, I think as this experiment, there will be improvement in accuracy when using word embeddings.
Yeah, any idea to improve the Sinhala word embedding and add it to your research? I mean, having trained your own word embedding maybe with more data than the one they have used.
Yeah, that's a great suggestion. I haven't thought about it before. I'll try to train them on our own word embedding and evaluate the result.
Okay, thank you, Bimsara. Any other questions from the audience? Okay, if not, let's say thank you for the presenter by giving a round of clap. And yeah, that's we came to the end of this particular session 4A on natural language processing. Thank you very much, all the participants. We presented 5 papers. Thank you especially all the presenters as well as the authors of the papers and all the participants who patiently wait more than I think 30 minutes more than the scheduled time. And also my team, thank you very much to make this session success and with some technical difficulties. So we will conclude the session. Thank you very much for all of you. The next NLP session 4C have already started. Unfortunately, we started it on 12:30, so you can move to that session immediately. And I will hand over the session to Kavinda. Thank you very much.
Thank you, Mr. W.V. Welgama and the authors who presented. So as said, we can move into the next item in the agenda. So we have two parallel sessions, session 4C on NLP and session 4D on machine learning. So hope to see you there and stay safe.